Hello everyone, good evening. Welcome to our presentation about shell and tube heat exchanger design. And we are group 13, and here is my group numbers. My name is Li Songran. My metric number is 191400.
My name is Mahfouz Alam. My matrix number is 195405.
My name is Fiza Shafi with matrix number 209424.
Okay, so for the objective of the project, design and choose a suitable heat exchanger to heat NaCl stream before it enters the reactors, and perform a simple mechanical design and simulation of heat exchanger. So for introduction, our design background is heating normal temperature as ethanol, and the raw ingredients is ethanol, and for heating ethanol at 25 degrees Celsius, and is a heat exchanger with hot water with 95 to produce, and heating the ethanol at 70. And here is our block diagram for the process details and the heat exchanger details we used. So why we choose the shell and tube heat exchanger? Because for internal detectability, more resistance to development of skills, like less frequency of cleaning compared with another type of heat exchangers. And the service life is extended, and when compared to the plant type heat exchangers, they are less costly, and for fluids are greater at operating temperatures and pressure, and easily handled. And last but not least, because pressure test is simple and tube leaks are quickly identified and required.
For the calculations, certain assumptions are made. We assume that thermophysical characteristics would remain constant and calculate thermophysical properties using mean temperature. The contaminants have no effect on the cold fluid's thermophysical characteristics. We assume the heat exchanger is in a constant condition. We suppose that the tube has thin walls. We assume that the shell wall is properly insulated in order to save thermal energy. We assume that the pressure decrease is minimal. We assume that any change in kinetic and potential energy are insignificant. In order to start with the calculation, 2 shell passes and 8 tube passes will be selected as the basic arrangement for the shell and tube heat exchanger. Here is the given data. The inlet temperature given is 25 degrees Celsius, whereas the outlet temperature given is 70 degrees Celsius. The total mass flow rate given is 2.1 kg per second. Molecular weight for ethyl alcohol is 46.07, whereas for H2O it's 18.02. For the calculation part, we calculate the log mean temperature difference using this relation, where delta T1 and delta T2 are the temperature differences between 2 fluids at the end of the heat exchanger. For the second step, we calculate the temperature difference delta T1, where delta H in is the inlet temperature of the water, and Tc out is the outlet temperature of ethyl alcohol, which comes out to be 25 degrees Celsius. Then we calculate the temperature difference of the 2 fluids delta T2. Here Th out is the outlet temperature of water, and Tc in is the inlet temperature of ethyl alcohol, which comes out to be 20 degrees Celsius. Then we calculate the log mean temperature of the heat exchanger by this relation, which comes out to be 22.407 degrees Celsius. After that, we calculate the heat. Transfer. Here, MC is the mass flow rate of ethyl alcohol. CPC is the specific heat of ethyl alcohol, and Q is the heat transfer rate. After calculation, it comes out to be 252.315 kilowatt. For the sixth step, we calculate the ratio of temperature difference by this relation. Here, small t represents the tube side temperature, and capital T represents the shell side temperature, which comes out to be 1.1. Then we obtain the correction factor from the correction factor F charts for common shell and tube and cross flow heat exchangers, that is 0.83. After that, we calculate the heat transfer surface area of the heat exchanger by this relation. Here, AS is the surface area of the heat exchanger and U is the overall heat transfer coefficient. Therefore, after the calculation, the heat transfer surface area of the heat exchanger is 14.28 meters square.
Thank you, Fiza. Now I'm going to present the symmetric diagram and prototype. So as you can see in the figure, so figure 1, symmetric diagram of shell and tube heat exchanger and the prototype. So prototype we use a plastic bottle, and we also shows in the image you can see tube inlet and tube outlet, also valve and others instrument we show in the image. And our in this design, so what water at 95 degrees Celsius is used to the heating source to achieve the desired supply temperature. So here you can see the AutoCAD design, the symmetric diagram, 2D design. So statistical analysis. For the statistical analysis, study is investigated the effect of mass flow rate on the overall heat transfer and the inlet of ethyl alcohol in the tube side on the log mean temperature difference and the surface area of the heat exchanger. For the simulation and the computation of the heat exchanger, we chose Microsoft Excel spreadsheet and the uploaded Excel on the Google Drive in the that which is group comprised of 3 sheets. So here the first sheet is variation of the inlet hot versus log mean temperature difference, and the second sheet is variation of hot inlet versus surface area, and the third sheet is the statistics sheet where we investigate the variation of 2 variables of heat exchanger. Simple linear regression. So here first which one is a simple linear regression. The most simple and common type of regression analysis is a simple linear regression. So here is a equation as you can see, and here is some others equation. So here is independent and dependent variables as you can see. So for the graph here, inlet temperature of ethyl alcohol versus surface area. So this graph is showing that the inlet temperature of ethyl alcohol is increasing with the heat transfer surface area of the heat exchanger, and the graph is above shows the how heat transfer surface area varies with changes in temperature. And the regression, you can see the regression value here, the coefficient of value is R square, which is 0.992, which is almost equal to 1. So which is good value, and our you can see the regression equation, which is y equal to 0.566. So here the polynomial regression. So for the polynomial regression, we here in the figure, which is inlet temperature of ethyl alcohol versus log mean temperature difference. So in this graph above shows that almost all the data is exactly on the second order polynomial regression, and the regression model obtained y equal to this equation, and the coefficient r equal to 1, which is very good. So from this data we know that the obtained coefficient which is exactly equal to 1. That means that I indicate that the value this one is very close together, and the equation which is quadratic equation, and this equation actually perfect for our statistical analysis. And for polynomial regression 2, so here is the another regression that is showing that mass flow rate is increasing with the heat transfer. So and the graph above shows almost exactly that is second order cubic equation. The previous one was quadratic, and this one is cubic regression, and the equation as you can see y equal to the equation, and the coefficient of the coefficient is determined r square equal to 1. So here from this value we know that the relationship between the mass flow rate and the heat transfer rate is modeled by the second order polynomial regression model. So that's it for me. I think now leave it with it.
For conclusion, finally, the developed shell and tube heat exchanger can conduct heat exchange. In the heat exchanger device, 25 degrees Celsius of ethanol is transferred from 95 hot water to optimal temperature of 70. We are able to build the most suitable heat exchanger for the whole project and investigate the important statistics analysis of the project. In the design of a heat exchanger, the heat transfer coefficient and pressure drop of the water heat exchanger must be carefully studied and considered. In general, increased heat transfer in the heat exchanger is accompanied by a rise in pressure drop, requiring higher pump power. Therefore, any benefits are improved. Heat exchanger heat transfer should be balanced against the resulting cost of reduced pressure. So here are some recommendation lists here, like increase the buffer spacing so that it flows slowly. This reduces the pressure drop on the shell side. And also like the number 3, by increasing the pipe spacing ratio, the cross flow velocity is lowered. And therefore the pressure drop on the shell side is memorized. Grid punches help minimize shell side pressure drop and security. And also like the number 4, increasing the buffer spacing so that the fluid flows slowly also can drop the pressure. So that's for the recommendation. So, and here is a reference that way to the design project refer journal, and here's the reference list. So thanks for your listening and have a good day. That's for our whole project presentation. Thank you.